This conference will now be recorded.
So, very good evening, students. Today, we are continuing the discussion on electromagnetic induction. So, there are many good problems in this particular topic, magnetic induction. So, many questions comes in various competitive exam. So, we have picked up various questions on this particular topic, where Faraday's law of induction, Lenz's law, Motional EMF, etc. will be discussed. Uh, so these are from JEE previous year's paper. Like this particular problem is picked up from JEE Mains 2020. JEE Mains 2020. So let us read the question and then try to solve it. An elliptical loop having resistance R. You can see that this is an elliptical loop which has major axis A, minor axis B, semi-major axis A, and it has resistance R. Semi-minor axis B is placed in the magnetic field as shown in the figure. So magnetic field is actually uh, along the direction perpendicular to the plane of this loop. As you see, the loop is in the xy plane, and magnetic field is along the z direction. With reference to this particular Cartesian coordinate, we can just make it out from here. If the loop is rotated about x-axis, if the loop is rotated about x-axis with an angular frequency omega, then what is the average power loss in the loop due to Joule heating? Since this loop is rotated, what is happening, when a particular area, like this magnetic fields are like this, so there is a flux links in this flux linked with this elliptical loop. Now when this is rotated about x-axis, then what is happening? The flux changes. What happens? Flux phi changes. Flux linked with this loop will be changing because you are just rotating along the x-axis like this. So sometime the number of flux lines will be more, then little bit lesser, and it will be like the flux linked to this loop will be changing with time as you rotate it with an angular frequency about this x-axis. Okay, so for this kind of problem, so the flux linked with this can be written as flux linked with the loop can be written as BA cos of theta. Why this cos theta? Why not only BA? I'll just explain you. Suppose magnetic field lines are like this, and there is some area like this. So it has area normal to like a vector, area vector, which is in this direction. Area vector is always normal to the plane of the loop. Okay, If this is rectangular loop, then its normal will be outward normal would be this way. Okay. So similarly, if this is elliptical orbit, so it can be either this way, the normal area normal, so area vector will be either this way or that way. Okay. So anyway, so this area vector, as you know, when the loop is rotated, see, loop will be sometime like this. It is now like this, but sometime it will be like this. Okay, since it is rotated, so the normal is, see, earlier normal was here, now normal will be here. Like that, the normal will be changing. Okay, or the area vector will be changing its direction, but the magnetic field is fixed. So in general, the magnetic flux is written as B dot A or B A cos theta. The theta is the angle between the magnetic field lines and the area normal. Okay, let us say this is the area normal and this is the angle theta with the magnetic field. Okay, now this theta, since it is rotating with angular frequency omega, we can write this theta is equal to omega into t. So I can just rewrite this flux to be so sometimes the loop will be like this, so that's how this area normal will be in this way. Okay, that's how I have drawn this. So theta can be written as omega t, so I can write this again as ba cos of omega t. Okay, now you know, here the question is the average power loss. So if you want to find out average power loss, either you have to find out P is equal to V square by R or I square R. What is this V? Let us this V actually is the induced EMF in this case. So what is induced EMF? How to find out induced EMF? Using Faraday's law with the Lenz's sign convention. Okay, so Faraday's law gives the EMF induced in the loop will be d phi by dt minus d phi by dt. That means you will get ba omega sine omega t. So this is the induced EMF. Okay, this is induced EMF. Okay, if we get induced EMF, what else we can find out? We can find out the current, or directly we can write down the power. So the power, since this elliptic loop has some resistance, so it will, so when the current will flow due to this induced EMF in it, there will be joule heating. So that's how the power loss will happen. So we can directly write this power loss. This is power, power. This EMF square by R. So EMF square by R means B square omega square A square sine square omega t. But what is this A divided by R? What is this A? A is the area of the elliptical loop. Area of elliptical loop. So this is given by pi into major axis into minor axis. So this is the area. So A square will be, if we put it here, B square omega square, then it will be pi square major axis square B square divided by R along with sine square omega t. I'll just remove this part. Rather, okay, I'm going to use this part now. So we'll write it here. Let us write the flux, induced flux minus d phi by dt here as ba omega sine omega t here. Okay, so this is what we are just carrying with this. Okay, after that, this is the thing. Now you have to find out average power loss. Average power loss means this. Okay, so average power loss, you look here, the power has b square, omega square, pi square, a square, b square by r. These are actually constant term. These are not changing with time, so I'll just keep like that. Okay, b square, omega square, pi square, a square, b square by r. Okay, now only thing is that we have to take the average of sine square omega t, and you know, when we take time average of this sine square or cos square within the full time period. Okay, so what will be the value of this sine square or cos square? I have been telling, sine square or cos square omega t average will be half. Okay, half. Always you can keep in mind that when we take average of sine square theta or cos square theta, that would give you half. I'm just directly writing it, b square omega square pi square a square b square by 2r. Okay, so this is average power loss in the loop. Okay, so I hope it is clear to you. So the option is, first option is the correct answer, not this one. There, the this is actually the total power, not the average power. This is average power. So option A will be correct answer for this question. So I'll just quickly summarize what were the key points over here. First of all, you have to write how to write for a rotating loop. You have to write the flux be a cos of omega t. Okay, then you have to find out the induced EMF, and once you find out induced EMF power, you can define E square by R. Here you have to find out average. So all other constants, all other parameters are constant other than the sine square theta, and time average of sine square theta or cos square theta is always half. So that's how we have reached to the answer. Okay, all right, so I'll just, if I write, okay, these are all, yeah, all right. So theta was also fine, theta is equal to omega t, so putting that, we have written that. Okay, all right, we'll move on to the next problem. So a copper wire, second problem says a copper wire is wound on a wooden frame. A copper wire is wound on a wooden frame. As wooden frame whose shape is that of equilateral triangle. You can see that this is an equilateral triangle. So wooden frame, this is a wooden frame, and there copper wire is wound like this. Okay, like this. Copper wire is wound like this. Okay, so like this it is wound. Anyway, so winding will be throughout the same direction. Generally windings are made like this in a same direction, so that the direction of the current will be the same to get the maximum flux or anything else, or magnetic field, etc. If you make like this and like this, so the direction of the magnetic field will be, like, current will be different, okay, opposite, then there may not be, the effective result may not be obtained in that case. Okay, all right, so this is an wooden frame in the shape of equilateral triangle as you see here, and a copper wire is wound over this wooden frame. If the linear dimension of each side is a, okay, side of the frame, suppose it is at it is a initially, then the dimension of each side is increased by a factor 3. That means earlier it was a, it is made to 3a. Okay, keeping the number of turns, see these turns are not increasing. Number of turns, if it were some n earlier. Now also it is the same. Number of keeping the number of turns of the coil per unit length of the frame is same. Okay. Then the self inductance of the coil, self inductance of the coil will be increased by a factor of 3, or decrease by a factor of this 9 into root 3, or will increase by a factor of 27, or will decrease by a factor of 9. So you have to answer this question. Okay, so how to solve this problem? I'll just make you clear again. So there is a copper wire which is wounded over a wooden frame which is in the shape of an equilateral triangle having side A, suppose in the beginning. Now the dimension of the wooden frame is increased. Dimension of the sides of the triangle is increased from A to 3A. A to 3A, keeping the number of turns of the coil per unit length of the frame same. Then how to, like, what will be the self inductance? Self inductance means L is equal to phi is equal to Li. Phi is equal to Li. So we know phi is equal to Li, where L is the self inductance. Okay, we have to find out the answer for this case. So this L for this particular or in any case, you know, like for loop you get mu n square A into L. Okay, what are these parameters? Mu naught is actually permeability in free space. N is the number of turns per unit length. A is the area, and the small l is the length of the length of each side. You may get it. Okay, so the total length of the wire. Okay, so here, as the total length of the wire will remain constant, since the number of turns per unit length is constant, so we can say L, suppose L1, this is the total length, 3A into N. This is same actually. It was earlier, so not L1, let us say this is L. So it is remaining constant. Now, if suppose the length, see the diameter, if suppose diameter is D, what is that? Diameter of what? Diameter of each winding. If diameter of each winding is D, each winding see here, this is the total number of winding. Total number of winding, I'm supposing. Total number of winding. Okay. So what will be the length? What will be the length of the winding? For each winding, what is the length? So length of each winding will be D into N. Okay. So diameter of, see, diameter like this. I have N windings and if the diameter of each winding is this d, then we can write approximately dn. D into n is the length of the winding. Okay, where length of the winding in the sense where the length of the the length where the windings are there actually. Okay, n windings are there, so the length of winding itself is d into n. Now self inductance, as we have written over here, it is, let me just use this space. So L will be mu 0 n square A into L. So here, what is A? A is the area of the wooden frame. Okay, after changing the dimension. All right. So we can write okay. Let us go with the side A itself. So mu 0, let this L be like that. So mu 0 L n square, mu 0 L n square into A. A is root over 3 by 4 into A square. Okay, A square. And okay, so now this L is again mu 0 n square mu 0 n square, then this factor 3 by 4 A square into D into N. Okay, so what we get from here is that these terms are constant. Okay, these are constant, this length. Okay, so these are constant. Let me write this. L actually is proportional to A square into N. This dN is the diameter and this N. Okay, so this is the number of turns, total turns. Okay, okay, so then again this N will be actually proportional to 1 by A. So if this is the case, this total N is proportional to 1 by A is the side, and L is directly proportional to A square and N. So if we just combine these two proportionalities, then what we get, is, after combining these proportionalities, we get the self inductance L is proportional to A. That means the self inductance is proportional to 3. sorry, proportional to the side of the uh, si side of the wooden frame. Okay, proportional to the dimension, actually, dimension of the wooden frame. And that's how we can say that the self inductance of the coil will be increased by a factor of 3. Okay, all right, so we'll go to the next. Then we'll go to the next question. So this question is very, very interesting, and uh, it will be a little lengthy. Let us see. There is a thin strip. This is also from 2000 JEE Mains 2019 paper. The previous problem was JEE Main 2019 itself. JEE Main 2019. So now we'll try to solve this problem. So this problem says a thin strip, as you see, this is the strip. It says a thin strip 10 centimeter long is on a U-shaped wire of negligible resistance. That means this U-shaped wire doesn't have any resistance. It is connected to a spring constant. See, this is a strip which has length 10 centimeter, as you see from the figure, and this strip is actually connected to a spring of spring constant. That means K is given 0.5 Newton per meter. Okay, and the assembly is kept in a uniform magnetic field B, magnetic field of 0.1 Tesla. Okay, if the strip is pulled from its equilibrium, so suppose this is the equilibrium, it is pulled in this way and released, a number of oscillation it performs before its amplitude decreases by a factor of E is n. Okay, see what will happen if you just pull it here and then leave it. It will start oscillating like this. Okay, as the spring is there, there will be oscillation. Okay, there will be an oscillation, and okay, let me just read the whole story here. So it will start oscillating. It says that if there is an oscillation, there will be amplitude of oscillation also. This amplitude, when it dies up to one, 1 over E times, then the oscillation number of oscillation is n. That means the amplitude of this oscillation will be equal to A by E when it completes n number of oscillations. Now if the mass of the strip is 50 gram, its resistance is 10 ohm, air drag is negligible, then what is the value of n? What is the number of oscillations you have to find out? Okay, so this is actually a very tricky problem and also lengthy. We'll just try to understand what is going to happen if this strip is pulled like this and release it. What will happen? There will be a simple harmonic oscillation, or an oscillation will actually initially there will be SHM SHM setup, right? Because there is a spring, there will be some oscillation. If I say simple harmonic oscillation in the beginning, it may be okay. Then what will happen, since there is a flux link in this, uh, that flux will change when it, see, if the amplitude is, see, suppose here is the equilibrium. So area, it when it just come close to this, then area is decreasing, and when it is going out, area is increasing. So in this way, actually the flux linked in this will be changing, and whenever there is a change in the flux, there will be induced EMF, and divided by R, there will be a current also. Okay, there will be current, induced current, which will be passing through this uh, strip. This is a metallic strip, so thin metallic strip. So current will flow in this. When current will flow, see, in when current will flow in this rod, any rod which is carrying a current I, suppose it has length L, and it is placed in a magnetic field, perpendicular magnetic field B, then this strip will actually experience a magnetic force which can be written as ILB or IBL, whatever you say. So as it uh, oscillates, it will actually experience a force due to this magnetic field, and also there will be induced EMF, as you know, induced EMF. That induced EMF will produce a current through this, and due to that current, you will be actually experience, this strip will experience a force that is called this, that is actually BIL. So there are, I'll just I'll just try to depict it here. What is happening? So there are two forces which are acting on this. One is the spring force. I'm writing as spring, F spring, and another force. This is actually force due to magnetism. So I'll write a B, due to magnetic field. So there are two forces acting on this. Okay. So net force F net. So this will actually be equal to MA. So F net is equal to M into A. So I can write, these are actually, if you just pull it this way, so spring force is this way, and also magnetic force will be in this way. So that's why I'm writing minus kx spring force minus magnetic force, that is BIL. Okay, BIL, or I can write capital L also, doesn't matter. So I can write BIL. So this is equal to MA. Okay. So now this I can write minus MA equal to 0. So let us see what all these things are. So this Kx, see, acceleration is actually d2x by dt square. Okay, acceleration we can replace with that. Then see this I, the current can be found out. Current can be found out. This I can be found out induced EMF by resistance, like writing like this. Okay, so what is induced EMF? This will be BVL. This has length L, suppose this strip has length L. So V is the speed with which this is actually moving, BVL by R. So if we put this, so let us say this B into L divided into I means B V L by R. So this BIL or IBL, this magnetic force can be written as B square L square by R into dx dt. That is V. V I am writing dx dt. So this BIL can be written as B square L square by R into dx dt. Okay. All right. I'll erase this part again. Now, x, this we can be keeping as it is. So this equation, suppose this is equation 1. So equation 1 can be written as m d2 x by dt square, taking minus common, plus b square L square by R dx dt, then plus k into x is equal to 0. So this equation, you can see this equation is nothing but an equation of a damped simple harmonic oscillation. This is equation number 2. It is an equation of a damped SHM, simple harmonic motion. Okay. So in this case, what we can do is, like we can just write down the amplitude, okay, from the knowledge we have obtained in oscillation part. From there, we can directly write the oscillation, like amplitude of the oscillation, to be A is equal to A0, that is the maximum amplitude, into e to the power, because this, like in case of damping, uh, the amplitude of the oscillation will be dying out like this, okay, exponentially. So that's why the solution, the amplitude can be written as A is equal to A0 B square L square by 2 into R into M. Okay. This, if you don't remember, please go and brush up this uh, damped oscillation. So from there we are writing this. Since we have got this equation, so from there we can directly write this uh, expression for the amplitude. Now see, in the question what was there, when the amplitude becomes A is equal to A0, it's A0 by this, okay, 1 by E0 factor of the maximum amplitude. So what is the condition? Okay, there will be T factor here. Okay, so let me go to the next page for this. So A is equal to A0 e to the power B square L square by 2 R and M into T. Okay, let us write this equation to be 3. I'm just making into two part of this space so that I can use. So look, for A is equal to A0 by E, T has to be equal to 2Rm. That means this power has to be 1. So that's why T has to be 2R into M divided by B square by L square. So you are basically finding out the time when the amplitude becomes a is equal to a0 by e. So that time you are finding. Okay. Now we have the values. We have all the values here. See, m of the strip is given as 50 gram. That means you can write this kg. R is given as 10 ohm. Okay. B is given as 0.1 Tesla, and L is given as 10 centimeter. That means 10 into 10 to the power minus 2 meter. If we put all these values, 2 into 10, then 50 into 10 to the power minus 3, and then b square 0.12 whole square, and L square, that means L to the power minus 1 whole square. If we do the calculation properly, this will give you second. So this will give you 10 to the power 4 second. Okay, 10 to the power 4 seconds you will get if you calculate properly. Now come to another point. See, we have to find out the number of oscillations. I have got total time. Okay, so oscillations means per unit time. Okay, oscillation, number of oscillation is actually the total time divided by time period. Okay, therefore we have to find out the time period. So what is the time period? Actually, time period is obtained from the spring force itself. So time period will be obtained from spring force. So from there, so 2 pi root over m by k. Okay, root over m by k. 2 pi root over m by k. So if we put these values, 2 pi root over m is 15 to 10 to the power minus 3 by k is 0.5 Newton per meter. So this will give you this much. Okay, you can see that. So this will be again this much second. Now then, what is the number of oscillations? So number of oscillations is obtained by dividing the total time divided by the time period, that is the time required for a complete oscillation. Okay, so we have got both. One is 10 to the power 4, another one is 2 pi root over 10. So so this will actually give you, so this actually nearly equal to 2. This will give you nearly 2. That means 10 to the power 4 divided by 2 number. This is a number, not. So this has also second, this also has second, so it is a dimensionless quantity. This will be a number per second. Generally oscillations is number per second. So this will give you 5, and that will 10 to the power 3. So this is the number of oscillations. See, then therefore after 5,000 oscillations, the amplitude of oscillation will be amplitude becomes a factor of a factor of factor of e. Okay, a factor of e. So this was the course like solution part for this particular problem. So what were the main points? You have to find out, like there is oscillation, etc. So you have to relate with this problem with simple harmonic oscillation somehow, and see there are, see, induction part here. Since there is a self-induced EMF, so that will actually create a current through this, and that current, again, this current carrying wire in a magnetic field will experience a force, that is also this BIL or IPL, whatever you write, that will be in this direction. If it is moved, if it is moving in this way, okay. And spring also will pull the strip in this way, so there will be another force kx. So both the forces we have got, and then we can write down an equation of motion, and from there we have written like we have obtained uh, the equation of motion to be a damped harmonic oscillation, like, yes, so representing damped harmonic oscillation, and from there we can directly write the amplitude of the oscillation. Okay, so after writing that, we are just applying the condition that for a is equal to a0 by t, a0 by e, the time will be this much. Okay, 2r m by b in b square into l square. So this much time will require. So then, if you want to find out the number of oscillations, then you have to find out the number of time period first. So time period can be obtained from the spring constant, like 2 pi root over m by k. So from there we will get the time period. Okay, so small t by capital T will give you the number of oscillations. Okay, all right. So here we will just solve another last problem. Uh, so look here, there is a metallic rod of length L. So this is a metallic rod of length L. It is tied with a string of length 2L. This is a string. This is a string which is insulating in nature, and there will be no induced EMF in this, or there will be no current in this string. Whatever will be there due to this rod itself. Flux will be linked with this rod itself. So this string is 12 in length, and this rod, metallic rod, is of length L. So let me just start from beginning again. A metallic rod of length small l, this one, is tied to a string of length 2L, this one, and it is made to rotate with angular speed omega. It is made to rotate with angular speed omega on a horizontal table, as you see in the figure. Okay, so one end of the string is fixed. That's how this is rotated. Okay, as you can see here. And if there is a vertical magnetic field, that means magnetic fields are going, okay, vertical. Anyway, you can take either going into the plane of this table, or coming out of the table, doesn't matter. But anyway, there will be a magnetic field which is vertical, perpendicular to the plane of this table. Okay, so basically then this rod is rotating with an angular speed omega in a region where there is a magnetic field. So that is the main problem over here. Okay, so what is the answer you have to find out here? The EMF induced across the end of the rod, there will be EMF induced. So that you have to find out. So here the options are given as, option A is saying 2b omega L square by, oh sorry, this is, yes, by 2. I don't know what is the logic. 2 can be striked out. Okay, so another option is, sorry, this is L cube, not L square. This is L cube. L cube. Second option is 3b omega L cube. Omega L cube by 2. Option C is 4b omega L square by 2. Okay, 2 are common in all the cases. And D is 5b omega L square by 2. So these are the options. Okay, you have to solve this problem. What is the problem? The rod of length L, metallic rod of length L, is tied with a string of length 2L, which is fixed at one end, and this rod, which is tied with the other end of the string, is rotated with angular speed omega. So what will be the induced EMF across this, across the length of the rod? So that is the question. So in this case, what we do generally, this is a motional EMF. We can write BVL. Okay, BVL. This is the main fundamental uh, formula which we are going to use for this particular case also. Okay, so let me show you a representative figure over here. So this is the string. One end of the string, suppose, is fixed to a particular uh, rigid object. Okay, so this is 2L. You can see that 2L length of the string, and I am just considering, and this much, this is actually total length is L, that's what is shown here. I'm considering a length, elemental length of thickness dx, as you see here, of thickness dx at a distance of x from this fixed end of the string. So from O to this dx, so this much is actually x, as you see from the figure, and thickness is given as dx. All right. So if you want to calculate induced EMF, then what you have to find out? See, induced EMF, as you said, we will be using this BBL. So the induced EMF will be E is equal to integration BVL. So here, if we put BVL, etc., then integration limit will be taken properly. So in this case, B, B is there, all right. So what is B? B we can write. See, each point of this rod is actually moving with omega angular velocity. So I can just find out linear velocity from there. So omega into x. V is equal to r omega, you know that. So from there we can find out here. So omega into x, and this L is fine. Okay, and this should be dx. B V L. L is dx. Sorry, this L is dx here. L is dx. Okay, L is dx. B V L. This is V and this is dx. Now you have to take integration limit on x. See, we need to find out EMF across the length of this rod itself. So this rod has length, see, from here. So 2L to, this is L, this is total L is 3L. So 2L to 3L. Okay, you have to take limit from 2L to 3L. Okay, this would give you the result. Let us see. So B omega, they are constant. So this will be x square by 2, x square by 2, where the limit will be 2L to 3L. So if you put the limits, so B omega into half. So this is 9L square minus 4L square. So this will give you 5 by 2 B omega L square. Okay, so look where here is the option. So the D, option D will be the correct answer for this question. So today we'll stop it here. We'll take up again more problems from this chapter, because this is really very, very important, and there will be many questions, as you see, in the competitive exam like JEE and other cases also. And this some cases problems will be really lengthy and tricky, so those things also will be solving. Okay, so thank you for your patience. We'll stop it here.